also it is called, as I have given the introduction yesterday about the subject, and the subject code is 18CV42. Okay, so subject code being 18CV42. What are the basics I will require here? We require your shear force and bending moment diagram, and all the basics of strength of materials. Okay, SOM. All the basics of SOM is a must over here, especially SFD-BMD, because how to draw. And when I go to SFD-BMD, we need to know how to find the reactions in case of a beam, unknown reactions, right? So when I talk of reactions, then we'll also come across the supports, the types of supports that are there, the types of loads that come over a beam, right? So these all basics are required when we are dealing with analysis of determinate structures. So that is why yesterday I asked you all to please brush up. If not, I will be doing it in between, so you all can go through. Okay. So coming next to okay, coming next, uh, we will just do some revision on reactions and support reactions and types of loads again today. So what is a beam? What is a beam?
Horizontal structure.
Horizontal structure. Anybody else? Yes, it is right. Not fully right, but yes, partially right. Anybody else? Any other answer?
Horizontal RCC member.
Horizontal RCC member. Okay. Both are partially right. It's a horizontal structural element. Okay. It's an element of a structure, a part of a structure. It is not a structure. Right? A beam is not a structure. It is a part of a structure. So it is a horizontal element. If this horizontal element, I will place it vertically, it becomes a column. Correct? Now, because it is horizontal, we call it as a beam, and else it is going to be a vertical element, meaning it is going to be a column. So, beam is a horizontal element of a structure or a horizontal structural element. Now, when we are talking of beams, we need to know its support conditions. How is it supported at the end? Support condition. So, yesterday we have seen if a beam is simply resting over a support, right? Like this. What type of support is this? What type of a support is this?
Fixed support.
Yes? Come again.
Simply support.
Simply support. Correct. It is a simply support, meaning the beam is simply resting over this. And yesterday we have seen in case of a simple support, the number of reaction R is going to be equal to 1. The total number of reaction for a simply support is R equal to 1, which is vertical because there is no permission for it to move in the vertical direction. Right? Then second, I will draw, we have a beam like this, and then it is placed on some support which is called rollers. So what type of a support is this? This is called as a roller support, right? So a roller support also will have reaction equal to 1, that is it is not permitted to move in the vertical direction. So R here also becomes equal to 1, correct? Then third, we have seen yesterday, what type of a support is this? The one which is drawn?
Hinged.
Yes, it is a hinged support, and the example for hinged support I gave yesterday was the door. So in case of a hinge, how many reactions are available?
2.
Yeah, 2 reactions. I just put off the fan. So you will have 2 reactions like this. One is going to be vertical, I call it RV. One is going to be horizontal, you can call it as RH, or some of them call this as RV and this as simply H. Okay, so we will have the total number of reactions equal to 2 in case of a hinged support. And lastly, we have, what type of support is this?
Cantilever.
It's a cantilever beam. Agree, cantilever beam. But what is the support name?
Fixed.
Fixed support. Yeah. This is a fixed support. And total number of reactions here is how much?
3.
3.
3.
So it is going to be a horizontal, a vertical, and a moment M. So R is equal to 3. So now you have seen the total number of reactions in each of these cases, right? These are your types of supports. Now, if they, on basis of this, I want to write the different types of beams. Okay, based on the supports, we will have the different types of beams. So, say I'll write, it's visible, yeah. Types of beams. So, the first one, you can have a simply supported beam. You will have a simply supported beam like this. Both the ends, it is simply resting. Both the ends of the beam is simply resting. So, in this case, what is the total number of reactions here? One is going to be here, another one is going to be here. So, total number of reactions is how much?
2.
2. R is 2. Second, if I have a hinge and I have a roller, okay, hinge will have how many reactions? A hinge is going to have 2 reactions and a roller is going to have 1 reaction. So, what is the total number of reactions? 3. Agree? Third one, if we have both hinges, a beam which has got end supports, both are hinges, what is the total number of reaction here?
4.
4, yeah, because here I'll have 2 and here I'll have 2. So total number of reactions here is going to be 4. So this is a simply supported beam. This is a one end hinge, one end roller beam. This is both the ends hinge beam. Then you have a cantilever beam. Correct? So one end is fixed, other end is going to be free. So what is the total number of reactions here? As good as only for a fixed beam. So that is equal to 3. The same cantilever, if at the free end, I will provide a simple support. Now, this is a cantilever beam. So at the end, I will provide a simple support like this. So what is the total number of reactions here now?
4.
4.
4. Okay. So this is called as a propped cantilever. Okay. It is also cantilever only, but it is called as a propped cantilever. This is a simple cantilever. Right? And these are based on the supports, the names. Now, why I have written these is, yesterday we also discussed the definition of determinate and indeterminate. Can anyone recall? What is determinate and what is indeterminate?
Determinate where we can find the reactions.
Yes, correct. And indeterminate where we cannot find the reactions. Right. Now to find the reactions, how many equations of equilibrium we have?
3.
3.
3. Yes. If we are able to find the reactions, okay, using the 3 equations of equilibrium, then it is a determinate structure. If it is not able to find, it is we cannot find the unknown reactions using the 3 equations of equilibrium, it becomes a indeterminate structure. Or one more methodology to find out is, if the unknown reactions R is less than or equal to 3, it becomes a determinate structure. And if R is greater than 3, it becomes a indeterminate structure. Now come back to this first one. Is it a determinate or indeterminate? R is 2.
Indeterminate.
Who is that? Indeterminate. Huh? This R is less than 3. So R is less than 3 is what?
Determinate.
Determinate. So this is determinate structure. What about next one?
Determinate.
R,
Determinate.
which is also
Determinate.
determinate. Yes. Third one, both sides hinge.
Indeterminate.
Indeterminate.
This
Indeterminate.
becomes a
Indeterminate.
indeterminate. Cantilever beam,
Determinate.
correct. And a propped cantilever,
Indeterminate.
Indeterminate.
right. So these are your determinate and indeterminate meaning, and based on the equations of equilibrium. Actually, module 1, you have something called as degrees of freedom, degrees of uh, kinetic indeterminacy, etc. The degrees of redundancy and degrees of freedom. But We are starting with module 5 because online classes are there. With what basics you have studied in strength of materials. With that, whatever is possible, we are doing that. And we'll come back. Module 1, we want to do it offline when college starts. If it doesn't start, then we will take it online only. But because this becomes easier, module 5, we are starting with module 5. Okay. Keep these basics in your mind. Again, I'll come back to this later. So according to this determinate and indeterminate, the entire subject where I say analysis of determinate structures, meaning we will be dealing with only wherein we will be able to find the reactions using the equations of equilibrium. Okay, is it clear? Now, if I want to talk about loads, types of loads, I will draw the loads and you tell me what type of load it is. Okay, so this is a beam and this is a load P. What type of a load is this?
Point load.
This is a point load. Correct. It can be like this or it can be like this also, right? At some angle theta. You all are not used to this, I think, much. So we will be taking this up also. So this is a point load. Second, you have a beam and I draw something like this. This is W per meter. What type of load is this?
UDL.
UDL.
What is the full form of UDL?
Uniformly distributed load.
Uniformly distributed load.
Yes, uniformly distributed, meaning the load is uniformly distributed in this much region. Okay, that is why its unit is W per meter. So W is what usually the load. So when I talk of P, it is going to be P kilonewton. That's why you write as 5 kilonewton, 10 kilonewtons like that. And when I have a UDL, it is going to be 5 kilonewton per meter, 10 kilonewton per meter, meaning for 1 meter, it is 10 kilonewton. And he will tell this is for say 5 meters, meaning for 1 meter it is 10, then for 5 meters how much? That is why you said 10 into 5. That's 50 kilonewton acting at the center of this, right? Then, okay, if I want to take up an example, I want to draw the free body diagram for this. Say I give you this is 3 meters, this is 1 meter, okay, and I give you here a load of 6 kilonewton per meter, right? UDL is 6 kilonewton, it is acting for a length of 3 meter, this 1 meter, nothing is there. So if I want to draw a free body for this, how do I draw? I will say 6 into 3. Am I right? Am I right? I do 6 into 3. That is going to be how much?
18.
18. And where will I place that 18? Can anyone tell me?
Center of 3 meter.
Center of 3 meter. I'll place it as here, 18 kilonewton. Do I write 18 kilonewton or 18 kilonewton per meter?
18 kilonewton.
Per meter.
Not per
18
meter, only
kilonewton.
18 kilonewton. How it is how to calculate the total load in case of UDL is, it is 6 kilonewton per meter acting for 3 meters. Okay, 3 meter. So 6 threes are, we do 18. Kilonewton per meter is multiplied with meter. So this meters goes and only kilonewton is there. So the unit tells me that only kilonewton means it has got reduced to a point load. Now this has become a point load. And where I place it is at the CG center. So UDL means how? It is something like a rectangular like this, right? So CG means at the center. That is why where we place it exactly at center, that is 3 by 2 meters from here. This is how we draw the free body diagram. So 6 into 3, whatever, or UDL load into its length and place it exactly at half the length at the center of that, and it would have been converted to a point load. So this is how we deal with the UDL loads. Okay. Next, I will draw the next one. This is a UDL. So we finished point load and uniformly distributed load. Third one, what type of loading is this?
UVL.
It
Uniformly
is
varying load.
correct. So you'll have a beam like this, A and B, and this is called as a UVL, that is uniformly varying load. It varies uniformly, not anyhow, up, down, nahi. Gradual. There is one pattern. Everywhere the slope is going to be same. So this is a uniformly varying load. At this junction, it is W kilonewton per meter. Okay, and it comes and becomes 0. But this is UVL. What is this then? Say this is W2 kilonewton per meter. This is W1 kilonewton per meter. So what is this then? This is UVL. ये वाला क्या है फिर?
Same, ma'am.
This is also UVL. So, but both are different, no, to look at. So, do I have any different names?
No, ma'am.
No. Everybody? Sure.
Trapezoidal and triangle, ma'am.
Exactly. So, this is going to be called as a triangular loading. And this is a trapezoidal loading. Because the shapes are like that. This is shape is a trapezoid, this is a triangle. So when we're dealing with a triangle, the load is given by half base into height, right? Total load is half base into height. Where does it act? It acts at 1/3 from the this 90 degree, that is base, and 2/3 from the apex of the triangle. And when we have a trapezoid, we break the trapezoid into a triangle and a rectangle. So triangle will have its loading here, that is half base into height, and the rectangle will be at the center with L by 2. I'll not go much into details of this because we'll not be dealing with this now. So these are the different types of loads that you will come across when you're drawing or when you have shear force bending moment diagram coming in the picture. Okay. Now we will take up a small beam and I want to find the reactions for the beam. So before that, what are the equations of equilibrium? Equations of equilibrium. How many equations are there?
3, ma'am.
3.
There are three equations of equilibrium. Which are those three?
Sigma fx is equal to 0.
Yes, summation sigma fx, so summation f of x is equal to 0, summation f of y equal to 0, and summation m equal to 0. Correct? Now, fx means all your horizontal forces. So when it is going from here to here, okay, I'll draw that later. So all horizontal forces are your summation f of x. All your vertical forces are coming under your summation f of y. And all the rotations are coming under summation m, that is movement. Now, what is the sign convention? To always remember the sign convention properly, simply you remember how you plot the graph in your high school. You used to plot the graph, no? This is your first quadrant, second quadrant, third quadrant, and fourth quadrant. Am I right?
Yes, ma'am.
Yeah. So this is your quadrant system. So here x is what? Positive or negative?
Positive.
What about y over here?
Positive.
Positive.
This side also y is positive. What about x over here? Negative. What
Negative.
about y over here? Negative. And this is also negative, and this is going to be positive. So why I drew this is, if your force is going like this, it is going in the first quadrant. So this is positive. If it is going like this, it is going in the second quadrant wherein it is negative. So generally we remember like this, plus, minus. Correct? It is nothing but based on your coordinate system or your graph what you draw. The same theory is applied. Then you have summation f of y's. If it is an upward force like this, your y is always positive. So upward forces you take as positive. Downward forces, you take it as negative. So downward is negative, upward is positive. Okay. Coming to rotation, if you have a clockwise, you take that as positive. If you have an anti-clockwise, you take that as negative. So positive is clockwise and negative is anti-clockwise. Okay. Anti-clockwise is also sometimes called as counter-clockwise. Okay. Anti-clockwise is also sometimes called as counter-clockwise. happened so that in the examination they used the term counterclockwise in one of the examples. And our students did not understand counterclockwise is what, because they didn't know what is counterclockwise. It is same as anticlockwise. Okay, negative. Now these are just a sign convention for us to follow when we are solving. Assumption. If somebody says, I don't want to go ahead with this, I will go with this as negative, this as positive, this as negative, and this as positive, and this as negative, and this as positive. There is no hard and fast rule. You can go like that also. Okay, it is your assumption. But whenever you assume something, say generally what I drew first, no, those are the assumptions what are made in all the textbooks also. But if you want to change the assumption and you want to solve, whenever you are solving, you will just show clockwise you are taking as negative. Any one you show, that would be sufficient. Clockwise you show that you are showing as negative, it is understood that anti-clockwise is positive. So these are just assumptions for us to solve. Ultimately answer would be same, only the signs would be different, but answer would be finally magnitude of the force only we are dealing with, no? So that doesn't much matter. So that was about sign convention. And clockwise, anti-clockwise, done. Do not mix your clockwise and anti-clockwise with your sagging and hogging of the beam. Okay, very important. Sagging, hogging is different, and clockwise, anti-clockwise is different. So whenever we deal with that, we will get back to that. Now I want to take a simple example. Say there is a beam, okay, and I have a UDL of 2 kilonewton per meter, and we have a point load of 10 kilonewton. This is 2 meters, 2 meters, and say this is 4 meters, or 6 meters. Right, this is your A, this is your B. I have shown directly simply support. If I want to show in terms of support system, then let this be a hinge and a roller. So support A is a hinge, support B is a roller. So at support A, how many reactions should I show in the free body diagram?
2 reactions.
2 reactions. So I want to draw the free body diagram to this. So this is your beam like this. This is point A. Okay. And at support A, I will show 2 reactions. Correct. I'll call this as RA and HA. RVA, RHA also is fine. Whatever you are comfortable, you take the name. Nomenclature, we are not much going to waste time. What you are comfortable with, you always take that. What about number of reactions at point B?
1.
1.
Number of reactions at point B is going to be 1, and I call this as RB. Okay. Then, so this is 6 meter and the remaining is 4. Here we have a point load of 10 kilonewtons. Point load will remain as a point load. Coming to UDL, there is 2 kilonewton per meter acting for 6 meters. So when I draw the total load, I want to draw the your free body diagram. So 2 into 6, that makes it 12 kilonewton acting at the center. So like this, I draw. This is 12 kilonewton and it acts at 3 meters, 3 meters, exactly at half. This is 2 meters, this is 2 meters is given. Any doubt with this? Am I on right track or something has gone wrong? Is it right?
Yes, ma'am.
Okay. Any doubts here?
No, ma'am.
Okay. Now I want to find the unknown reactions. Which are my unknown reactions? HA, RA, and RB. Now to find these unknown reactions, I have to apply the conditions of equilibrium. Which condition of equilibrium shall we take first? Yes?
Effects.
Fx.
Fx. So I'll say summation f of x equal to 0. How many horizontal forces are there in our equation in this free body diagram? Only one, yeah. That is HA. Nothing else is 0, so nothing else is present, so equal to 0. So HA value is 0. Okay. Let us go to the next equation. Condition of equation of equilibrium or condition of equilibrium. Summation f of y. Meaning all the vertical forces. So you have a RA upwards. You have a 12 coming down. You have a 10 coming down. And you have a RB going on top. Right. Now, RA when I write, it is plus RA or minus RA?
Plus.
Plus.
plus RA. What about 12?
Plus. Minus.
minus
Minus 12. What about 10?
minus
Minus 10.
Minus 10 and plus RB equal
RB.
to 0. Right? So I will get an equation. RA plus RB is equal to 22 kilonewtons. Right? So this is from my second equation of equilibrium, we got this equation. Call this as one of the equations. Let us apply the third condition, that is summation M either at A or at B. Thumb rule, or generally what I do is I take always left hand side or left support moments, because loads will give you all clockwise and reactions will give you anti-clockwise. I am used to taking at left support. If you want to take right support moment also is fine. Nothing is wrong in that. Okay, I will take it summation MA equal to 0. You can write summation MB also. So when I'm taking moment at this, HA is passing through this point, RA is passing through this point. So are they giving any moments? Do we have any moments because of RA and HA?
No, ma'am. Zero.
No. So 0.
No, ma'am.
What about 12?
3 into 12.
Yeah. 12, 3 into 12 will go according to the moment formula. I will write the formula. Moment is given by what? F into D. Force into perpendicular distance. Okay. So always mention the force first and then the distance. So when I'm writing moment at A, 12 is the force, distance is 3. All right. 12 into 3. Now this is clockwise or anti-clockwise?
Clockwise.
It is plus. So plus 12 into 3. Next. 10 into this distance also is going to be clockwise. So 10 into what is this distance? 3 plus 3 plus 2. So plus 3, 6 plus 2 is 8. So plus 10 into 8. Correct? Then I have RB. RB into the span. And RB will give me clockwise or anti-clockwise?
Clockwise.
Anti-clockwise. So minus RB into total span is how much? 10. Equal to 0. This is 6 plus 4 is 10. So this is your equation. 12 3s are 36 plus 8 into 10, 80. This I will send it to the right hand side. It becomes how much? 10 times of RB. Now 80 plus 36. How much? 100 and
16.
116 equal to 10 RB. Or what is the value of RB? RB is going to be 116 divided by 10. That makes it how much?
11.6.
6.
Kilonewton. So RB value is 11.6 kilonewton. Therefore, we know that RA plus RB is 22 from your equation 1. Correct? Therefore, RA would be 22 minus RB, that is 22 minus
10.4.
10.4 kilonewton.
4.
Correct? Yeah. So 10.4 kilonewton. So you got a value of RB to be 11.6 kilonewton, and you got a value of RA to be 10.4 kilonewton. So this is what we did. We found the reactions. After finding the reactions, we will be usually, if it is a shear force bending moment diagram, then we will go for shear force and bending moment, finding the shear force bending moment, finding the stresses in the beams, etc. So any doubts with this? Whenever we have such numerical, I will be solving it in detail. Do not worry. But I will also expect you also to put in efforts. Any doubt with this part?
No, ma'am.
No.
No,
So
ma'am.
this was about finding the reactions using the three equations of equilibrium. Right. Now I will be beginning with our actual module 5, because I will require these basics. That's why I did that. Module 5, that is arches and cables. Arches and cable structures. I was not able to draw diagrams yesterday because I was not using a board. So I will be pretty much be able to draw the diagram now. You must have come across, there will be hilly area like this, and there would be a water or usually bridge or over bridge like that. If say there is water over here and they want to construct they want to make a lane on this, right? They will either a bridge or a railway track it could be, correct? So I'll just draw a diagram. So okay, something like this it goes, and then I will have something like this. Okay, if you have seen this, so then it will be having such cross sections. Have you seen? It will be circle like this here. इसके ऊपर से you will have that pathway for the train or the road, etc. But basically, what I am more interested in is this curve. Have you noticed this curve anywhere? Or even the tunnels, when you have this cross section of a road you have, and you will have this tunnel. Have you seen why this shape is given to it? Tunnel, why don't I give a square opening to a tunnel? Why do I have to give a circular opening? I mean, this, any guesses? At least have you observed this curve or this curve?
ma'am.
Observe, no? If you are not able to talk or not in a in a place where you can unmute and talk, or you are shy, not to unmute and talk, I would love even if you drop the messages chat box. Mein. Have you seen such structures?
Yes, ma'am.
Yes, ma'am.
Yeah. So this is called as an arch. Okay. This is called as an arch. Now, just out of track for you to more understand where you must have seen this. PUC students who have studied, okay, dance you have not studied yet. Okay. Have you seen that? I think Dhoom 3, Amir Khan. Have you seen the movie Dhoom 3, Amir Khan's double role?
Yes,
Katrina Kaif? No, there's
Ma'am.
nobody on. Huh?
Yes, ma'am.
You all have seen. Okay. At least somebody has seen. The last 5-10 minutes of the movie where he dies, they both die from a bridge, no? That is a dam top head. Have you seen? It is a curved dam. Or have you observed? If not, today you go after the class, probably YouTube and check out. That is an arch dam. There is a dam, arch dam it is. Okay. Idukki Dam in Kerala. Kerala, okay. That arch action say they are controlling the pressure of the water. All of you are aware of dam. Now, what happens in a dam? There is a river flowing. He will construct a structure across the river to stop the flow of the river so that they will save the water. Okay, this would be you know the terms. This is called as upstream side. This is called as a downstream side. There will be gates over here, and the excess water will be flowing from here. Something like this. So the side of the dam, I'm looking from the top. Okay, so the side of the dam, what is happening? There is enormous pressure built up. Agree, because the water is standing, and this pressure is going to be it is going to be uh, held back, or the pressure's resistance for the pressure is by this dam structure. So dam could be anything. It could be a earthen dam, it could be a concrete dam. Similarly, like this, there is this Idukki dam which is in arch shape. This dam, what they have done is they have built it like this in an arch shape, and this is the water which is standing. This arch is taking care of the pressure that is coming over here. I think you must have studied this in your BMCT somewhere, Building Materials and Construction Technology, third semester subject था ना ये BMCT?
Ma'am.
Yes,
So
ma'am.
arch section you have not studied there?
Ma'am. We studied, ma'am.
So what is the importance of arch? Studied, no? So the same arch section will be used over here. Okay. Now why arch? Or what happens if when I have a regular beam? So now when we are talking of the load that is applied, when we are talking, say you take a beam, simple beam, when we are talking of the transfer of the load in beams, usually the reaction, what the output, or how the beam is going to, what are the parameters we are going to consider from the beam would be the bending moment and the shear force. Meaning, whatever is the type of the beam and whatever is the type of the loading, ultimately, what am I interested in at the end? The bending moment and shear force when I'm dealing with the beam, because these two are directly used for the design purpose. So when you do the analysis, third semester also, SOM, when you did, you analyzed the beam for a given type of a loading and you put up a bending moment and a shear force diagram for it, right? So based on that, I will be picking the bending moment and shear force value because it is needed for me in my design, RCC design of that particular beam. So those are the outputs. Okay. Now, what happens if the span is too much? Distance span. What is span? Between 2 points. No. So if the distance between two ends is too much, in that case, if I'm going to give a horizontal beam, it is not going to withstand that. Okay, for larger spans, beams are very uneconomical because they are very thin and they won't be able to take that load. The self weight of the beam only contributes towards the stress, right? So what they do when there are larger spans like this, long distances, for in case of bridges and all, arches are provided. These are the arches. Arches are provided instead of beams. Arches are nothing but curved beams only. You have a beam like this, so the same beam only in a curved manner it will be provided. Arches are nothing but they're the curved beams in vertical plane. Why vertical plane? Now the curve is in what direction? This direction. No? It is going like this. So this plane may. So this is what plane? This is the vertical plane. So the arches are the curved beams in the vertical plane, and the transfer of load takes place like this only, on this curved action only. Okay. So this is a cross section. Simple diagram I'll not again draw. So this is how, if I take a general example. So from here to here, I'll call this as a span of the arch, right? So from this point to this point, it is the span of the arch. And then here at this point, you will have abutments. You will have abutments. And then the topmost point over here, it is the topmost point in the arch. This is called as a crown. You know crown? A king wears a crown like that. So crown is always put up on the head, no? So the topmost point is called as a crown. And then if at this junction I draw a line, so from here to here, this is the rise height of this particular uh, arch. So this is the rise, this is the crown, this is the abutment, and you will have at the abutment positions only something called as springings. Okay, here also you will have something called as springings, wherein those and abutments are together. So springing and abutments are together. So arches transfer loads to the abutment. So from the arch it goes to the abutment at the springing points. So the points where arches are ending are called as springing. From there it is going down to the abutments. Clear? So here at this junction, I can provide what type of support is hinges. So the type of support that can be provided at the springing is hinges, meaning we will be encountering hinge kind of support when we are solving the numericals for arches. Okay. So are the terminologies clear? Any doubts with the terminologies? Next, what are the different types of reactions that are coming? Now, whenever I take a term named reaction, uh, what is a reaction according to you? Can anyone tell me? What do you understand by reaction? What is a reaction? There is a table.
Opposition for the motion.
Yes, yes, come again.
Opposition for the movement.
Exactly. Opposition. Okay. So reaction can be more defined from your Newton's third law. What is Newton's third law? Every action has equal and opposite reaction. Correct? That term is coming over there. So, say there is a table and I'm keeping a box on a table. I place a box on a table. Now, the box is going to have some weight W, correct? And it is going to act at this point, the CG of that. So, when the weight is acting on the table is going to produce an equal and opposite reaction R, which has got the same magnitude as that of W. The magnitude is going to remain same, meaning if you are applying a 10 kg box you are keeping on the table, the reaction also would be 10 kg only, but in opposite direction. And this is a reaction. Also, from Newton's third law, when I say for every action there is equal and opposite reaction. So any kind of forces that are coming over the beam is going to respond back. It is going to give back basically. That is the reaction. So the reactions could be, I can call not the general your end support reactions. Apart from that, in generalized, if I talk, the reaction could be the shear force, bending moment, the stresses that are getting induced. Those are also reactions only because of the type of the loading, type of the support, type of the beam. The different stresses are coming into the beam, correct? So those are all are going to be your reactions. So in a beam, when we are dealing, you all have seen in third semester SAM, I will be dealing when even if it is stresses, bending moment, shear force, and stresses. So now how it takes place in case of a arched beam. You have a arched beam like this. So in a arched beam, say your there is a hinge provided. The arch at any section, if I'm going to cut any section in the, if this is the arch beam like this entire beam, I take a section anywhere. At any section, it is going to be subjected to three important things. What are those? One is going to be a normal thrust, a next radial shear, and third one is going to be a bending moment. So general, your regular beams that you have come across, that is going to be having a shear force and a bending moment, generally. But when we have a curved beam like this, so it will have a normal thrust, meaning N normal to the, I will draw the diagram. Then radial shear, because the moment I say it is curved, there is some kind of radius coming into picture, correct? So there is going to be a radial shear and a bending moment that is going to come into account. So if I draw a cut section of the arched beam like this, say, so at this junction, if I want to show these three forces, then here you will have your normal thrust N, okay, and radial shear is denoted by Q. Normal thrust is denoted by N, radial shear by Q. So radial shear means it will be along the radius. So along the radius, something like this, no, radial shear. So here Q, radial shear, and then you will have a rotation, okay, that is your bending moment. So these three things will be present in the arch or a radial beam. Because of the curved nature of the arches, they give rise to horizontal forces also. Now because this is a curve, so there comes or they induce horizontal forces also. That is why I said you will have a hinge, because hinge will have a horizontal and a vertical, correct? So horizontal forces are also encountered in the arches, okay? Abutments, whenever after this bottom pay there is abutment, no, they go and they touch the abutment. So these abutments are basically going to be designed for these horizontal forces. Now when we are dealing with the types of arches, how many types of arches are there, what kinds of arches are there, because we have this for our syllabus module 5 that only. So first time, it is a three-hinged arch. Okay, meaning this is one hinge, this is one hinge, and this three-hinged arch. 1, 2, 3. At a crown, there will be a hinge provided. Okay, so this is a three-hinged arch. Second type is a two-hinged arch, meaning only like this, hinges provided at the both ends. Sorry, here and here. No hinge at the crown. So this is a three hinged, 1, 2, 3. This is a two hinged, only these two. And third one is going to be hingeless. Hingeless arch of 6 support or fixed arch, you can say. So something like this, and both the ends it is going to be fixed. So this is hingeless. Both our ends are fixed. This is hingeless. 3 hinge, 2 hinge, and this. You have these for your this you have for your solving. Okay, I mean for your syllabus. So a 3 hinged arch is a determinate structure. It falls under a determinate structure. 2 hinged arch is a indeterminate, and this is also indeterminate. So these two are not there for your syllabus. Only you have 3 hinged arch because it is a determinate structure, and your title of the subject is ADS, analysis of determinate. So we will be dealing with only determinate structures. So 3 hinged arch is a determinate, so we will be going with 3 hinged arches only. Any doubt till now, till this point?
No, ma'am.
No, ma'am.
No. Shall I take, because actually class is from 3 to 5, but I can't take it only for 1 hour also, and I can't take till 5 also because I know it is difficult for you. Another 15-20 minutes, shall we continue?
Yes, ma'am.
Yes, ma'am.
Ma'am.
Yeah. So I will give the introduction of 3 hinged arch and the new formulas for that. So the next class onwards, we'll take the numericals. Okay. So now when we are dealing, as you have for your syllabus, 3 hinged arch. Okay. Is there for your syllabus? In this, there are two types again. 3 hinged arch could be of two types. One is circular, and the second one would be parabolic. Okay, one is circular and one is parabolic arch. So these two types are there for your syllabus for solving. Yeah. So first one, if I take a circular arch, this circular arch, I will give you notes of this. Okay, I have written down the notes. I will be scanning those and I will be sharing. As and when we finish the class, I will scan those notes and I will forward it to you. So when I'm dealing with a circular arch, let me draw a circle. So something like this and here. Okay. So here you will have your crown. So what I do, I'll call this point as A and B, and here are your hinges provided. So I'll draw a hinge at this junction A and B, and this is your rise. Let us call it as H. So height or H or rise you can call it. This total from here to here, let it be L. So this would be L by 2, this would be L by 2, half of each. Okay. Now this is say the diameter, and somewhere here is the center of the circle. So from here you will have, if I draw like this dotted, it is the R, that is the radius of that particular circle. So this total height is nothing but the diameter, that is nothing but 2 times the radius. So in this 2 times of radius, if this is H, what is the remaining height? Remaining would be 2 times R minus H. Agree? 2 times R minus H, because this is 2 times R and this is H. So 2 times R minus H is this remaining distance. So that is 2 times R minus H. Let this angle be theta. Okay. And here I will consider a point D. So this A, B, C is the crown. Let us be C. And let us take a point D at this junction. And these coordinates I want. Coordinate means what? It is at what distance? X and Y from some particular support. So what do? We will drop a perpendicular from here. From this, let this be Y. And when it this perpendicular, this would be X. Okay. So this is the figure. If this radius I want to what? Radius is like this R and at an angle theta. So I have to resolve this radius. So you will have R cos theta and R sine theta coming into picture. This is going to be R sine theta. Here you will have R cos theta. Are you aware of how to do the resolution of a force? Okay, I'm just taking 2 minutes outside this derivation. You have a force F given, which is making some angle theta like this. Okay, so if I'm breaking this force F into two mutually perpendicular forces, this is called as resolution of a force. Okay, wherein we break one force into two mutually perpendicular forces. That is this, and they both will be having a 90-degree between them. Now, wherever is the theta, there the cos goes. F cos theta, F sin theta, like this. If the same force F is given with theta in the vertical, okay, now I will break the forces this and this. So now theta is with y-axis, so I'll have F cos theta. Cos goes with wherever the theta is, and this becomes F sin theta. Okay, so generally we go with this. So based on this, again, you have sign convention. This is nothing but your quadrant system only. So you have a force over here. I will resolve it like this. You have a force in the second quadrant. You will resolve it like this. You have a force in third quadrant. You are going to resolve it like this. And you have a force in the fourth quadrant in this manner. So say these all x's are thetas, all x-axis. So this is f cos theta, f sin theta, same. Cos, sin, cos, sin. These are all your thetas. Based on this, you will have sign convention. This is going to be plus, this is going to be plus, minus, plus, minus, 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 and plus. So based on this, we will be writing the sign convention, and this is called as a resolution of a force. So coming back to our derivation. So if this is the radius and this is the theta, here is going to be my cos term coming, and here is going to be my sine term coming, r sine theta and r cos theta. Okay, so this is the diagram. Now from the property of a circle, okay, the radius of the circular arch of the span L and rise h may be found as follows. Meaning what we will do, now this is our base, no, span. So this is one remaining part of the diameter, this is the remaining part of the diameter. So from the property of circle, this into this is going to be equal to this into this. Okay, so we will make it, write it down, that is L by 2 into L by 2, that is this into this is going to be equal to this into this. How we have similar triangles rule, no, like that. So this is nothing but H into the other part is going to be 2R minus H. Simple. Length in, L by 2 into L by 2 is going to be equal to H into this. Okay. So now this becomes what? L square by 4 is equal to 2RH minus H square. I open the brackets. I get this equation. Now I'll take the H over here. L square by 4 plus H square is equal to 2RH. I want the equation for radius. So what I'll do, I'll keep R over here. 2 and H I'll take this side, and the LCM. I'll get ultimately R equal to L square by 8H plus H by 2. So this is the value of the radius over here. Okay. Nothing. Only trick is this into this is equal to this into this. You should know this is the span total L. So this is L by 2, L by 2. Height, riser or rise of the crown. So H, so remaining would be 2R minus H. Keep that in mind, multiply that, you get the condition or equation for the radius R. Okay. Now consider a support A as the origin. Here is the support A, this is the support B. So if I consider support A as the origin, the coordinates of the point, meaning this X and Y, no, I have to find the coordinates. So X can be written as L by 2 minus R sine theta, and Y can be written as R cos theta minus R minus H. Or, okay, it's not visible for you, I'll write it here. First, I'll write what we got R. We found R as L square by 8H plus H by 2. We have found this. And then we are, when we write for X and Y, the coordinates, this X and this Y. So X is given by L by 2 minus R sine theta. So I said, no, this is R sine theta, this is R cos theta. When I resolve this radius R and with respect to this theta. So L by 2 minus R sine theta is your X. Similarly, Y would be H minus, sorry, not H minus, total, that is R cos theta. This is R cos theta minus R minus H. Okay, if I open these brackets, I will have H minus R into 1 minus cos of theta. This is Y, X and Y. You can directly, you remember these as your formula, or you anytime can draw this and write this is your sine and this is your cos. So from there you will get the coordinates of x and y. In case of what? This is a circular arch. Okay, we are dealing with circular arch. Once this is done, then if I want to apply the same thing for parabolic arch, say second part be parabolic. In parabolic arch, I will not, the figure and all will not change much. Only thing is, it is going to be like this. Here you have your A hinge. This is the hinge that is B. Here is your C with another hinge at that point. This was your D point, the same figure I'm drawing upper part. This distance is your Y and this distance is your X. Only thing is that here only you will have X and Y. Your coordinate system is going to be here, X and Y. So parabolic equation I have to make use of. What is a parabolic equation? That is in case of parabolic arch, taking this as the origin point. From the parabolic equations, it is 4hx divided by L square into L minus x. Okay, h being this and this is the length. Okay, this is x, this is y. So 4hx by L square into L minus x. Now this is your parabolic equation. Okay, from the general law of parabolic equations, you are able to write that in terms of R case, that is H and L case. Now, if the crown is taken, if I take crown as the origin, now I took this as origin, this became X and Y. If I take crown as the origin, the equation of the parabola reduces to. So, if C is the origin, okay, then equation of parabola is reducing to x square by y is equal to a. Don't break your head much. Finally, ultimately, whatever is the formula, we will be making use of that only, but you should know how to do this, where a is nothing but a constant. This is the parabolic law. Now, in parabola, I have two cases again. These two are in same level, or I can have a condition where they both are at different levels like this. So there is difference in the levels, no? So in parabolic or even in circular, at same level, arch or abutments or springing points at same level, meaning at same heights, or at different level, that is different heights. There are two conditions. We have to apply this, that is x square by y equal to a parabolic law to both of these conditions. So next, if I'm writing that condition, say there's a bit of theory here, meaning derivation. Try to understand this video. I'll be sharing another half an hour after the class. I will be sharing the video on the YouTube also. So that link will be given to you. You can go through the video again. Okay. So if springing points are on same level, same level, not visible, meaning same, like this only. So this one, they both are in same level, A and B. This was your C, here you had D, etc. This is your length, L, right? If both are on same level and our equation is x square by y equal to x square by y equal to A, I have to apply now. So what I do, x becomes equal to what? X becomes equal to L by 2 and y becomes equal to h, meaning if I take C as the origin now, C points becomes my origin. So this is x, this is y. So x becomes L by 2, y becomes h. Initial diagram when I had drawn, I told you to take the origin as this point, A point as origin. So when A point was origin, you had that y equal to 4hx by L square into L minus x. But now when I change the origin point to this, my x value becomes L by 2, y value becomes h. And these two values I will put over here. Simple. So therefore, x square by y equal to a is going to become equal to L by 2 the whole square divided by h square equal to a. That is nothing but L square by 4h equal to a. Okay. So a, that is your constant value is L square by 4h now. Where this goes? Here. Back to that. Therefore, a equal to L square by 4h. I will put in x square by, it's not visible. x squared by y equal to L squared by 4h. This is the condition when they are at same levels. Okay. Try to grasp how much is possible. When we are doing the numericals, this concept will be more clear, right? And before starting the numericals, I will be again once drawing all the diagrams and explaining only the formulae so that you will be able to apply the formula. Second case, if springing points are on different level. Okay, different level means what, Baba? Like this. Here is one hinge. Here is one hinge. This is your crown. Like this. So what I'll have now, from here to the crown, there is one height. I call that H1. From here to the crown, I have another height. I call it H2. This becomes L1 and this becomes L2. Okay, L1 and L2. Total is L only. Total is L, which is L1 plus L2. But for this side, it is H1 and L1. This side, it is H2 and L2. So these are at different level. That is, let H1 and H2 be the depth of the apartments from the crown. Let L be the span. Now we know the condition, that is x square by y equal to constant, that is A, right? So we know this condition. So this condition, if I take a square root of this, if I take a square root, x by under root y, it will still remain a constant only, because after taking the square root, I will have constant side, that side also same. So I will now we make use of this, that is x by root of y as constant. Apply this on A point, apply this on B point. So when I apply this on A point, so constant becomes equal to x means L1 divided by y is this distance. That is, somebody is joining. Okay, that is y is h1 under root of h1. Similarly, I can also write for the other part. So x becomes L2, y becomes h2. L2 by h2. Okay, so this together, if I want to write for the entire parabolic curve, then it is going to be L1 plus L2 divided by under root, sorry, h1 plus under root h2. Okay, L1 plus L2 is what? L. So then it becomes L divided by under root h1 plus under root h2. Okay, I've applied this rule separately for this rule separately for this, added them both. So I'm getting this condition. From this is what? This is nothing but constant. I can again go back to this and get L1 value and L2 value, where it is going to be L under root h1 divided by h1 plus h2, and L2 is going to be L h2 h1 plus h2 with this. Okay, so these are the equations that we will be making use of. So do not worry if you're not understanding for now. I will again explain only the formulas and how we apply these formulas, where it is used, etc. when we are dealing with the numericals. Clear? If I say any doubts, you will say no. But I'm sure this entire thing would have been a doubt only to you. So tomorrow's class, we have something called as, we will be dealing with the static loads that are coming over the, what, your arch. For example, static loads and dynamic loads, what is the difference? So this is your arch. And I have a crown. I have a hinge here also, here also, here also. This is A, this is B, this is C. Okay. And because it is a hinge, it will have HA horizontal and VA vertical. It will have HB and VB vertical, and at the crown. Okay. I want to find at a point D the X and Y. So the loading would be given like this. They would have given a W1, W2, W3, all point loads, and a UDL for the rest with W per meter. So static loading. Now we have to write the set of equations when the curved beam or the arch is under the static loading as shown in the figure. Okay, so for this, what we will be applying? We will be applying the conditions of equilibrium, that is summation f(x) equal to 0, summation f of y equal to 0, and summation m equal to 0, and we will be considering, I told no, normal thrust. What are the three things that we have to search or find in case of arches? Is your normal thrust, which is n, and then you have radial shear. Yes, anybody's got any doubt? Yeah, radial shear is q, and what else is there? Normal thrust, radial shear, and vertical shear. Vertical shear also you can write, or the other nomenclature also is fine. So there are equations for these three, and once we it takes 5 minutes, we'll write the equations for these three, and then those equations will be applied to the numericals, and we have to find these three, that is the normal thrust, radial shear, and vertical shear for the given example. So tomorrow onwards we will go with numerical. Whatever derivations I did, I know 90% of whoever is present in the class, it was not very clear or you did not understand, but it is basics. If you understood, well and good, else also it's okay. I will again teach you if you have not understood, and this video also will be circulated. Okay, so tomorrow's class, directly formulas for this and the numericals I will be dealing with. Is it okay?
Yes, ma'am.
So shall we stop for today? If you have not understood the derivation, no, do not wait. I'll stop the recording first.